Well, hi there guys. We're having another look today at vector equations, parametric equations, as we described them in the last video. This is the second in the series of 4 on vector calculus, and today we're specifically looking at position vectors as a function of time. The parameter today is time, okay? So let's see what we can find out. We're going to be looking at Cartesian paths and collisions and all kinds of fun and thrills and spills. So we're saying here that here is a position vector. R is the traditional term to give it, with a vector underneath, and it's a function of t for time. Okay, so the first function f1 of t in the I direction, and the second function in terms of t in the j direction, and t refers to time. Okay, no surprises there. Now, we basically have a position vector here, as I was saying, which changes with time. It changes with time. So by substituting a value of t into the equation for r of t, we get a particular value of the position vector at that time. Well, no surprises there either. Therefore, this equation then can be used to track the actual trajectory of the particle in real time, because we have the x function in terms of time, and independently we have the y function in terms of time. Time is very much in the picture here, so therefore we can work out the x and the y position at any time, t being the parameter, time, and we can check the actual trajectory of the particle. Okay, if we convert this parametric equation, in which you know the parameter is t, because I've said that about 3 times so far, into a Cartesian equation, that's just x and y equals f of x, then the time information is lost. I know it's very sad, but it is lost. So the Cartesian graph then shows y versus x, which is the snail trail, or just basically the trace of where the trajectory has been after it's made its journey, with no time information of when or how fast that trajectory was created. I know, it's a bit sad to lose that information, isn't it? But nevertheless, that's what we do. So r of t, now, for example, r of t would be cos t plus sine t, cos ti plus sine tj. That would be the equation of a circle in terms of our x's and our y's. X would be cos t, t is greater than or equal to 0. Y would be sine t, t is greater than or equal to 0. That is the parametric equation, you better believe it. And this is the time information about x, and that is the time information about y. And the Cartesian trail of y versus x with no real-time information at all given to us is this baby here, x squared plus y squared equals 1. All you can see is the line of where it's been, not where it started, not its trajectory, not anything else, but just the snail trail of where it's been. Okay, now I've explained all that before, but that's just a recap, okay, to give it a bit of reinforcement. E.g., an example here, the vector equation, the position at any time t, minus cos of 2 pi t in the I direction, plus sine of 2 pi t in the j direction. Again, that's a circle, guys. Again, describes a particle moving around the circle, but with the following features. Now, at time t is 0. If you plug that into there, okay, you'll get cos of 0 is 1, so it'll be minus 1. And if you plug 0 into there, you'll get 0. So it starts its journey at the position x is minus 1 and y is 0. Okay, that's what the time information gives you. The particle moves on the curve with equation x squared plus y squared equals 1. Yes, we can see that. The particle moves in a clockwise direction. You can actually work that out, as I'll explain to you later, by then substituting in here a quarter cycle, a quarter of the period of this thing. Now, the period of that thing is 2 pi over this number. 2 pi over 2 pi is 1, so the period is 1. So you'd check in at a quarter of a cycle, which would be t is a quarter, and you'd see what the position is, first the x, then the y, then plot the coordinate points x, y on a Cartesian graph plane, and you would get the position after a quarter of a cycle, and that'll tell you which direction it's going in relative to the starting point at minus 1 and 0. We'll go through that in more detail later as we go through these examples. Yes, the particle moves around the circle with a period of 1 unit. I already worked that out, didn't I? Yes. Okay, now here's an example. Let's get into it. Sketch the path of a particle where the position at time t is given by that equation, that vector parametric equation. T is the parameter, t is time, this is x, that is y. Looks like a quadratic to me. Let's go for it and see whether we can prove that it is. Okay, here we go. What do we just got to sketch the path. All right. X is 2t, y is t squared. You get that, don't you? Yes, now we're going to eliminate t. For you and me, from equation 1 we know that t is x over 2, and we substitute that little equation there, t equals x over 2, into here, okay? And what are you going to get? You're going to get y is x squared over 4. That is a parabola. You'd have to be a little bit careful with this parabola because you have to work out what the domain of these things are. The domain of them, and I was explaining that at great length in the last video, because they can be restricted functions, and in fact this is very much a restricted function. It's not just your common or garden y equals x squared over 4, guys. You've got to look back and see what the restrictions are, or the domain of t is, because that affects x, which is a crucially important thing, and it also affects y, but the domain of the Cartesian is the possible values that x can have, which emanate from the possible values of t. So if t has got to be greater than or equal to 0, therefore x has to be greater than or equal to 0. So therefore, guys, we've only got the right-hand side of our parabola, haven't we? We certainly do. So there it is. See, now you'd be wrong if you plotted the whole parabola willy-nilly without thinking about that. See how important it is? You've got to always have a very close look at your parameter and the possible values that it can have, and therefore the values which it gives rise to in terms of x. And you might as well work out y while you're at it, just for reasonableness check. But the x is the crucially important bit, okay, in terms of your domain of your Cartesian. Now NB for you and me, this is very, very interesting. Say, for example, I gave you another parametric equation here where x was t over 2 this time, and not 2t, and y was t squared over 16. Now, if you basically do the same exercise that I just went through over there and get yourself a Cartesian relation here, you would get exactly the same y equals x squared over 4 as what I got over here, okay? So, yeah, I know, that's confusing, isn't it? In fact, ladies and gentlemen, there are infinitely many possible parametric equations for x and y which give the same Cartesian result. That is a mind blower. And the reason for that is that they just happen at a different speed and a different rate according to the time information, but they all leave the same snail trail, okay, or vapor trail. Yeah? Alright, now we're going to have a look at this one now. This one looks very interesting. Let's have a look. We've got to get the describing the motion of this object. Okay. It's got a cos t for the x, it's got a sin t for the j, and it's even got a k, a z bit. Looks like it's stuck up in the air, 2 units, vertically up off the Cartesian plane. This is time. Well, I think, ladies and gentlemen, this is a circular motion, aka what we've already been talking about previously to this, and it's basically sitting up in the air by 2 units. But let's just show you. We'll go through the process. It is described in 3 dimensions with components I, j and k directions. The k component does not change with time, so the particle is permanently displaced by 2 units in the positive k direction at right angles to the xy plane, sitting up in the air like on the top of a flagpole kind of thing, and moving around in a nice neat circle centered around the origin is my tip. Regarding the xy plane, yes, x is cos t, y is sin t, therefore sin t squared, or sin squared t plus cos squared t equals 1. Substitute for x and y, and we've got that. Of course it's a circle. Centre on the origin, radius 1, but it's just stuck up in the air by 2 units. Now we've got to look for the direction of the motion. Now this is the interesting bit here. You've got to substitute 2 values of t in here and look at its Cartesian position, and then work out what it's doing relative to its starting position. Alright? Now, I'll show you what I mean, okay? Now, x is cos t, y is sin t, you know that. Now, when t is 0, that's my first reference point. If you work out what cos t is for t is 0, that'll be 1, because cos of 0 is 1. The y position will be sine of naught, which will be naught. So it starts off when t is naught, or at the start of its journey, at the coordinate position 1 and naught. X is 1, y is naught. Now let's go now for a quarter cycle. At a quarter of a cycle, for this thing which has a period of just 2 pi, okay, the coefficient of the t term here is just 1, so therefore it's got a period of 2 pi. Therefore, after a quarter of a cycle, which is t being the value pi over 2, we know that therefore x would be cos of pi on 2, which would be 0, right? And y would be sine of pi on 2, which would be 1. Therefore, the new position after a quarter of a cycle, guys, is where x is 0 and y is 1. Now, let's have a look at this. The plot thickens. Here is a graph, and we're going to show you. That's where it starts, and that's where it is at a quarter of a cycle. Okay, so you can see which direction this thing is moving in. It's moving that away, which is anti-clockwise. Okay. Now, incidentally, while we're on the subject of working out the direction of travel, please don't pick a half a cycle rather than a quarter of a cycle, because if you pick half a cycle, you get an ambiguous result. It'll be halfway around its circular journey and you won't know how it got there. So don't use half a cycle, use a quarter of a cycle, all right? Now, therefore, we're just about getting to the end of this. There it is. There's the beast there. It's going round in a circle like that, anti-clockwise, like that, and it's stuck 2 units up in the air. Yeah? Oh, there it is. Very nice. Okay, you happy? Yeah, nice and simple. Now, this is the most interesting question, and this is something you really, really have to come to grips with. This is about particles which collide in part A and particles who do not collide, but their paths just cross. Now, that might confuse you, so I'll explain that a little bit in a moment. And see the distance between the particles when t is 1. Now, this is a bit of a graphic illustration, but if you think of an intersection, and perish the thought, 2 cars which collide at an intersection, and we don't want that to happen. They would be at the same coordinate points, x and y, at the same time, wouldn't they? Yes, they would be. In order that they would touch each other, they would have to be. Now, in terms of something which their paths just cross, that could apply to 2 cars going through an intersection and crossing the exact same coordinate points, but at different times. Their paths cross, but at different times. That's what we mean by paths crossing, at different times. Okay, so that is the difference. It's a dramatic difference. Okay, it makes all the difference to the way you do this calculation. Now here comes A. All right, there is that's R1 of t, and here is R2 of t. 2 different paths, right? 2 different particles, 2 different beasties. Now, we have to get them to collide, okay? And we have to get the point at which the particles collide. Well, in order to do that, guys, we're going to first of all have to get the time that they collide. So, as I said just earlier in the preamble to this question, if the particles collide, they are both at the same place at the same time, yes? Okay, so therefore, we're saying that this is, wait a minute, this is x1 from particle 1, position 1, that's x1. This one here is x2, this one here is y1, this one here is y2. So what we're saying is x1 has to be equal to x2, y1 has to be equal to y2, and of course at the same time means that t1 has to be the same as t2. Okay, you get that? Okay, so I'm just going to call it t because they are the same time. I'm going to drop the subscripts for the t1 and the t2. We'll just call it t because that implies you're talking about the same variable, which means that they're going to be getting to the same place at the same time. So here is my, now what's that? Is that my x1? That's my x1 equals x2. And here comes my y1 equals my y2. Now, what I'm going to do, ladies and gentlemen, is I'm going to solve those. I'm going to solve this one for t, and I'm going to solve this one for t, and I have to make sure that the t values I get out of both of those solutions are going to be the same value, okay? The same value. In other words, x1 equals x2, y1 equals y2 at the same time, okay? So let's do that. From equation 1, what am I getting there? Oh, look, that was easy, wasn't it? Goodness, it's only a linear one, isn't it? Okay, so it looks like that. Yes, I can see that's right. T equals 5. Now, from equation 2, that'll be a little bit more involved because that's a quadratic. Yes, so we're saying, therefore, x1 equals x2 at t equals 5, aren't we? Yes. Now, here comes the second one. Okay, t squared minus 7t plus 10 equals 0. I've just got it all over the one side of the equation, which is very easy to solve. My goodness. Therefore, t equals 5 or t equals 2. Now, we've got two solutions out of here. Two solutions. So, you've got to pick the solution where the time is the same for both these scenarios. This one was t equals 5. This one was t equals 2 or 5. Okay, that means that the y1 will be the same as the y2 at two different times, 5 seconds and 2 seconds. But at 5 seconds, the x coordinates are also equal. They're at the same x position at 5 seconds. So obviously guys, yes, that's for the y's. So therefore we want x1 equals x2 and y1 equals y2 to be both happening at the same time, which must be therefore t is 5 is the only possibility. Alright, so t is 5 is the time at which those two paths collide or coincide with their x and y coordinates, yes? Now we're going to check the answer, see if we're right. If you plug in t is 5 into R1, you'll get 7i plus 35j, and if you plug it into R2, my goodness me, such ecstasy and joy and rapture. We've got it, we've got it. So that is the position at which they both collide at time 5 seconds. Okay, now they want the point, so the point is going to be at that point there, or if they asked you for a coordinate point, then you could say open bracket 7, 35 close bracket. But that's good enough for me. That's the point of collision. Okay, you get it? Yeah, nice, isn't it? Now here comes B. Now this is the very, very big difference in approach that we use for when the paths cross, because paths cross means that it doesn't have to be the same time anymore, does it? No. So if the particles cross paths, they are at the same place but at different times, yes? So what we're going to do is we're going to say, therefore, x1 equals x2, y1 equals y2, but t1 does not equal t2, right? So now I'm saying this is my x1, that's my x2, yes, that's that, and then I'm saying there is my y1 and there is my y2. Now I'm not going to call them the same thing anymore. I'm not going to call t1 equal to t2 like I did over here. Where was it? There. I just called them the same thing, didn't I? Because the t1 was equal to t2. Well, I'm not going to do the same thing over here. I've got these two separate equations, in two unknowns now, t1 and t2. Okay? And we're going to solve those simultaneously and work out the times at which the paths cross. Okay? And then we're going to work out the point that represents, yes, like we did up here with this 7i plus 35j for when they collided. Okay, so from 1, I'm just solving simultaneously here, and then I'm going to crunch through the algebra. So t2 is 2t1 minus 5, and I'm going to sub that into the second equation, and that's going to get me that. Now, I can solve it now for t1, and then I can solve it, sub back and get t2, and then we'll work out what those positions are. Hopefully they'll come out to be the same, otherwise we better rethink what we're doing here, guys. So that's yes, does that look right? Yes, yes it does. It does. Right, oh, and 9 5s are 45, all goodness, I'm getting excited. And 9 and 5 are 14, so therefore t is 5 or t is 9, right? Now that's when the paths cross, and we happen to know that this one was one of the times when their paths crossed, but at the same time, yes. But this one is a new arrival on the scene here. T is 9, okay, and therefore T2 is 5. Oh yeah, when you solve back for T2, you'll get 5 or 13. Okay, so the 5s work out. We know that's when they collided, right? It's just coming out in this solution as well, okay? And therefore, when T1 is 9, that'll have this certain position, and when T2 is 13, we should have the same position. That's how it should work. So we better check that out. Over the page we go. Right, so when x1 equals x2 and y1 equals y2, t1 equals 5, t2 equals 5. That's the collision which we found earlier. Now, when t1's 9 and t2's 13, the paths cross at different times. Let's check that answer, as I said. Okay, so t1 at 9, r1 I mean, at 9 seconds, plugging that into our position vector, our r1 position vector, 15i plus 91j, and for particle 2 at 13 seconds, if we plug that 13 seconds into the equation for its position vector as a function of time, with t equals 13 in there, what are we going to get? Oh, yes. 15i plus 91j, hey, yay today, hooray, we got it. And therefore, the point of the paths crossing, not at the same time, is 15i plus 91j. And the first one got there at 9 seconds, and the second particle got there at 13 seconds. And that is it, guys. Yes, it's mighty fine, isn't it? Absolutely tops. Now, part C is a little bit of an anticlimax here. It's just the distance between the particles when t equals 1. Well, that's very easy. We've just got to sub in t as 1 into the first one, and then the second one. That's what you get for the first particle. Second particle, we get that, and therefore that's its position. That's particle 1 at t is 1. That's particle 2 at t is 1. Now, Pythagoras, are you awake? Aha, he's here. Pythagoras' theorem to the rescue, the distance between 2 points. This is something you learn in year 9. So it's basically the square root of this coordinate minus this coordinate all squared, plus this coordinate minus this coordinate all squared. And we get 4 root 2. Woohoo! For me and you, we did it. That's the distance between the particles at t is 1 second. And huzzah, huzzah, hurrah! You'll go far. So go ahead and practice, do a wonderful job with it, and have a marvellous time, because it is really, really good fun. Okay, all the best. Have a wonderful day. We'll see you next time.